In this example problem, we're going to calculate the stresses at service for the section shown below with a composite cast-in-place topping. So we have our non-composite section, which is a double T and 8 double T 24, and we have a 2-inch topping on top of that double T. You can see some of our non-composite section properties are given. These were taken from the PCI design handbook. And then we have our material properties, including our creep and shrinkage coefficients. These I'm giving to you, but you could use any creep and shrinkage equations, ACI or AASHTO to calculate those. We're also given our effective modulus for our pre-stressing, which takes into account the effects of strand relaxation. You can see here we have a self-weight moment given, a moment due to the topping or deck given, and a live load moment given, but no axial loads in this problem. Our first step is to find our transform section properties, and we'll need to find our modulus for our girder concrete. So we have 5,000 PSI concrete for our girder or beam, so that'll give us a modulus of 4,031 KSI. We need to find the modulus for our deck. Again, using the ACI expression, we can find the modulus for our deck, which has a concrete strength of 3,000 PSI, gives us a modulus of 3,122 KSI. And then we can find our effective modulus using our creep coefficient, just by taking the modulus for our beam concrete, 4,031 KSI, divided by 1 plus the creep coefficient, 1.8. So that gives us our effective modulus of 1,439 KSI. And again, this takes into account the effects of creep. Next, we need to find all of our material properties and our modular ratios. So we'll use the moduluses that we found on the previous slide to calculate our modular ratios. Our short-term and long-term modular ratios, so the way that we transform our pre-stressing strands into an equivalent area, are the same as some of our previous examples. So we just take for short-term, we take our pre-stressing stiffness divided by the stiffness of our beam concrete. And for the long-term, we need to take the effective stiffness of the strand divided by the effective stiffness of the concrete. So that takes into account the effects of strand relaxation and creep in the concrete. For the deck modular ratio, we take the modulus for our deck, which is 3,122 KSI, and we divide this by the stiffness of our beam concrete, 4,031 KSI. So this will give us a modular ratio here of 0.77. So when we're finding our composite section properties, we're going to transform our deck area using that modular ratio 0.77. For our long-term non-composite transform section properties, we'll use the same procedure that we'd used in previous examples. So I'll go through this quickly. So for our transformed area, we just take our gross area plus n long-term minus 1 times our pre-stress area, and that gives us our long-term transformed area. For our centroid from the top, for our long-term non-composite section, we can take A times Y top for the gross area times n minus 1 times the area of our pre-stressing times the distance from the top of our beam section to the centroid of our strands, 20 inches. And then we can divide that by our transformed area. So that gives us 7.4 inches. And just note that this is from the top of the beam, the precast beam. So not the top of the deck yet. So at this point, we're not including the deck or topping. We can now find our long-term transform moment of inertia, the same way that we have in the previous example, just by taking our I gross times our AD squared component for our gross section, And then we have our AD squared component for our pre-stressing strands. And that'll give us a long-term transformed moment of inertia of 23,788 inches to the fourth. And again, this is for our non-composite section. So now we have all of our long-term non-composite section properties, and now we need to calculate our short-term composite transform section properties. And these short-term composite transform section properties we'll use when we're finding the stresses caused by live loads. So first we need to find the composite section height. And to do this, we'll take our 24 inches, which is the height of the beam, plus 2 inches, the height or thickness of the topping, which will give us a total composite section height of 26 inches. Our deck area is just our 2-inch topping thickness times 96 inches for the width of the topping, which will be 192 inches to the fourth. The deck moment of inertia is going to be the width of the topping, 96 inches, times 2 inches to the third divided by 12, which will give us a value of 64 square inches, or inches to the fourth. And then the distance from the bottom of our section to the centroid of the deck is going to be our height of the beam, 24 inches, plus 2-inch deck or topping thickness divided by 2. And that'll give us a height here of 25 inches. So now with these properties for our deck, we can find the short-term composite transform section properties. And we'll start by finding our transformed area. So our transformed area, AC transformed, is going to be equal to our gross area, 401 square inches, plus our short-term modular ratio, 7.07 for our pre-stressing, minus 1, times the area of our pre-stressing, 0.918, plus 0.77, the modular ratio for our deck, times 192 inches squared, will give us an area here of 553 or 55.3 inches squared. So this here is our composite transformed area. Now we can find the transform centroid, and we're going to measure this from the bottom of the section so that there's no confusion of whether we're measuring from the top of the deck or the top of the beam. So this is from the bottom of the precast beam. So we'll start. We have our YB composite transformed equal to our gross area, 401 inches squared, times the distance between the bottom and the centroid of our gross area, 17.15 inches, plus our short-term modular ratio for our pre-stressing, 7.07 minus 1, times our pre-stress area, 0.918, times our YP, so the distance from the bottom to the centroid of our pre-stressing strands, 24 minus 20 is 4 inches there. And then we'll take 0.77, we're transforming the area of our deck, times 192 square inches, times the distance from the bottom to the centroid of the deck, 25 inches. And then all of this is going to be divided by our composite transformed area, which we found to be 555.3 inches squared. So this will give us a value here of 19.1 inches. So now we can find the distance between the centroid and the top of the deck. So this will be our 26 inches, our composite height, minus 19.1 inches, which will just be 6.9. Then the distance from the centroid to the top of our precast beam, we have that 24-inch gross height minus the 19.1, will give us a value of 4.9 here. And then we can also calculate our transformed moment of inertia. So again, we're going to use parallel axis theorem. and we'll have two additional terms. We'll have the transform moment of inertia of our deck and the transformed AD squared component for our deck as well. So plugging in these values, we'll get an I composite transformed equal to gross moment of inertia 20,985 inches to the fourth, plus our AD squared component, so 401 inches squared times 19.1 minus 17.15 squared, plus our AD squared component for our transform pre-stressing, 7.07 minus 1 times the area, 0.918, times 19.1 minus 4 squared. And then we have our deck components. So 0.77 times the moment of inertia for our deck, 64 inches to the fourth. And then our AD squared component for the deck. So 0.77 times 192. The area of the deck times 19.1 minus 25 squared. So this will give us a composite transformed moment of inertia of 29,007 inches to the fourth. So these are the section properties that we'll use to resist the live load on the next couple slides. Our next step is to find our decompression force and decompression moment using the equations that we had found before in class. So starting with our decompression force, our N naught sub S is going to be equal to our EP effective 27,930 KSI times our locked in pre-stressing strain, 6.8 times 10 to the negative third, times the area of our pre-stressing, 0.918 inches squared. And then we subtract off our effective concrete modulus, 1,439 KSI, times our shrinkage strain, which is going to be, it's negative for compression, so negative 3.0 times 10 to the negative fourth, and then times our gross area, 401 inches squared. So this will give us an N naught sub S of 347.5 kips. Our M naught sub S is going to be equal to 27,930 times our locked in pre-stressing strain, 6.8 times 10 to the negative third, times our area of pre-stressing, 0.918, times dP minus YT transformed, so the distance between the centroid of the section and the centroid of our strands, 20 inches minus 7.4. And then plus our effective modulus for our concrete, 1,439 KSI, times our shrinkage strain, negative 3 times 10 to the negative fourth, times our gross area, 401, and then times 7.4 minus 6.85 inches. So this is going to give us an M not sustained equal to 2,108 kip inches. So this will be the M naught sustained that we use and the N naught sustained that we use on the next couple steps. Note that for our live load, We're already taking into account the effects of our pre-stressing and our shrinkage into our M0 sustained and N0 sustained. So our N0 and M0 live load are going to both be equal to 0 here. We can now find our strain at the centroid and our curvature from our applied moment and our axial loads. We'll start with the strain at the centroid due to our sustained loads. So here we have no sustained axial load, but we have our N sub naught equal sustained equal to 347.5 kips divided by 1,439 KSI times our A transformed long term, 417.9 square inches. So we'll get a strain here of negative 5.78 times 10 to the negative fourth. You can see we don't have any applied axial load, so this strain at the centroid due to our live load is going to be equal to 0. Then we can plug in our values to find our curvature due to our sustained loads. So we had 1,440 kip inches, our applied sustained loads, or moment from our applied sustained loads, minus 2,108 kip inches, our M0 sub s, times 1,439 KSI. EC effective times 23,788 inches to the fourth, which gives us a curvature here of negative 1.95 times 10 to the negative fifth radians per inch. We can plug in our values for our live load curvature as well. Remember, our M not sub live load is going to be equal to 0 because we're already taking into account our pre-stressing effects in with our sustained loads. And then we're going to use our I composite transform short term here because our live load is resisted by our composite section. So we can find our live load curvature then to be equal to 1.85 times 10 to the negative fifth radians per inch. So these are the strains at the centroid and the curvatures that we'll use to calculate our strains and our stresses on the next couple slides. We will first find all of our strains and our stresses due to our sustained loads. We can see that on the previous slide we had a negative curvature, which means that our curvature is going to add compression at the bottom and tension at the top. So we'll have a larger compression strain at the bottom and a smaller compression strain or tension strain at the top fiber. So we'll have a curvature diagram shown here. And we can go through and use our strain at the centroid, our curvature, and the distance between the centroid and our extreme tension and compression fiber, or top and bottom fibers, to find all of our strains and stresses. So to start with our top fiber stress, and again, we're going to look at the top of our non-composite section or our precast section. We have our strain at the centroid minus our curvature times the distance between the centroid and the top of our precast section. And we'll find a strain here of a negative 4.34 times 10 to the negative fourth. We can take this strain minus our shrinkage strain, so minus a minus gives us a plus here, and then times our effective modulus for our concrete to get the stress at the top of our precast section due to all of our sustained loads. We can do the same thing for the bottom of our precast section, and we'll find a stress as shown here. So negative 0.19 KSI at the top and negative 0.87 KSI at the bottom. We can do the same thing to calculate the strain at the centroid of our pre-stressing. We need to add in our locked-in strain differential to this strain, which will give us a total strain here of about 6 times 10 to the negative third. And then we take that times our effective modulus for our pre-stressing to get the stress in the pre-stressing due to all of our sustained loads. So 166.9 KSI. Next, we can find all of our strains and stresses due to our live loads. You can note the one difference here, or one of the differences, is we need to find the strains and the stresses at the top of the deck, at the top of the beam, and at the bottom of the beam. So we have an additional strain and stress component here. So you can see we don't have any strain at the centroid, so all these centroid strains are going to be equal to 0. So we just have our strain due to our curvature. So we have our curvature times our distance components from the centroid of our composite transform section to the top of our section to get the strain at the top. And then we just take that strain times our modulus to get the stress at the top. We can do the same thing with a different distance component to get the stress at the top of our beam, our precast beam. So you can see that right there. And we can do the same thing with, again, a different distance component to get the stress at the bottom of our beam. So we can see that we have a tensile stress at the bottom equal to 1.42. And then we can do the same thing to figure out the strain and the stress in our pre-stressing. So strain and times the modulus will give us the stress in our pre-stressing equal to 8 KSI. So these are all the strains and stresses from just all of our live loads. And we need to combine these stresses with the stresses from our sustained loads to get the total stresses on our precast, or on our composite section. Our last step is to combine all the stresses that we found. We can combine the stresses at the top of the deck, at the top of our precast beam, and at the bottom of the precast beam. We have no stress due to our sustained loads at the top of our deck because only our live loads are applied to our composite section. So we'll get a stress at the top of the deck equal to negative 0.51 KSI. When we add the stresses together at the top of the beam, we'll have our sustained stresses and our live load stresses to get the total stress at the top of the beam, the precast beam, equal to negative 0.56 KSI. We can add together our stresses at the bottom of the beam, at the bottom of the section. So our compression from our sustained loads or tension from our live loads, which will give us a total stress here of 0.56 KSI. And we can compare this value here to the tensile strength of the concrete and see that our applied stress is greater than the tensile strength of the concrete. So we would expect the section to crack. So this would not meet our stress limit checks. Finally, we could check the stress in the pre-stressing by adding our sustained stresses to our live load stresses to get a total stress in the pre-stressing of 173 KSI. This is less than the yield strength of our pre-stressing, so we would expect our steel or pre-stressing to still be in that linear elastic range. And this concludes this example problem. Note that you can also find release stresses using a similar procedure, only with release concrete strength and self-weight forces. I do this in another example problem, but we won't do that in this example problem just to keep this problem shorter.